I wonder if that's different.
Yes, so since you use this number down here, I just relooked with your number, so it's all good. Okay. There's a slight error.
I like the idea of -4. I want for that. I don't see, I'm not loving the way we're incorporating this. Oh, I was really bad. I like you, oh, maybe I don't like this. Okay, I actually don't want to do this, so I think you can just do it on the table. I actually just had it. But I think there's like a really nice thing to say. That's me, all the way.
Doesn't matter. Whatever you want.
You will lose it. Um, thank you. And then there's, I'm not living that triangle, and I would check your receipts if I do that every month. Yes, you have to have all of those right. Oh my gosh. Yes, I was outside number something. Working with about 3 minutes to go.
Really?
Time flies when you're having fun.
Unless you're having anxiety, it's not.
Same thing.
I guess being controlled is that.
Mm-hmm. You'll need that today. How's your hot pocket?
Good.
Good. Yeah. Mm-hmm. What's the derivative of x to the eighth?
All right, I'm gonna put up the timer for 2 minutes. It better be in my hands in 2 minutes or I don't want it. Nope. I can give you 0. I don't want that for it. Hello. What's the girl in the
Oh.
Yeah.
Yeah. I don't think
You said this thing is calculator, right?
there, you don't have any like calculus shown on your. Thank you. All right, less than 60 seconds to have your test in my hand. If you have an extra sheet of paper, just throw it on that. I'm gonna let you do that.
Yeah.
Oh, yeah. I also forgot to bring my time. I'm almost done. I think I'm going to pass. No, I'm not. Oh, yeah, I did that too. I did that too. Thank you. Oh, yeah. How fun.
All right, 5 seconds. Give me your test.
I have all of my answers, not all of them.
Give me your test.
Okay. Did you have yellow?
Really?
Or did you have purple? I picked purple one. I had all good. I turned it off. There's one question that had so much yellow and I didn't understand what the yellow was for. Yellow was simple.
All right, as you get back in your desk group, what I need you to do is find your notes from last time. Yo, Lily, in the chat, can you hear me? Sick. All right, I don't know where my mic is, but I'm gonna try this out. Let me know if it's annoying. All right, so we are gonna work through two. Oh wait, I need to switch my screen. Goodness gracious. Yeah, absolutely. Let's get this guy.
I've been a couple really sick.
Yeah.
I was like,
All right, my goal is to get these graded by next week because I would like you to be able to see those grades before you go into winter break. I have an idea. We'll talk about the other assessment at the end of class. So my goal today is to show you two different models that can be modeled by differential equations. One is one that we probably talked about in Algebra 2 called exponential growth and decay. Maybe not your Algebra 2 because your Algebra 2 was an interesting year. And then we're going to talk about logistic differential equations. So hopefully you have your 5.2 notes from last time. Those were the ones where we talked about solving separable differential equations. We're going to solve a particular, not like a particular solution, but a specific differential equation. And to the point where we're going to essentially memorize the solution of this guy. Because you've really already seen it before. Oh, should we do the Algebra 1 problem I did today?
Yeah. Yeah.
We really don't have time to do it, but we can try. Let's see how long it takes you. All right. I have a handful of money. There's only nickels and dimes in my hand. I have 12 coins and 95 cents. How many nickels, how many dimes? There's only one answer.
How many cents?
95. We'll put the 5. You got it?
I guess.
You have a guess? I don't want guesses. I want answers. That doesn't answer 12 coins.
I have 7 dimes, 5 nickels.
7 dimes, 5 nickels, 70 cents and 25 cents. That works.
Yes, that's what I got.
Win to Nick.
Yay.
Also, all right, so what I would like to do off of the 5.2 notes, we're literally going to do 2 questions. We are going to write this as a differential equation. We are going to solve it. And then we are going to do this question about fruit flies, which is, in a word, thrilling. So let's go ahead and we're going to solve this differential equation. I can tell you, you've probably seen the solution before. Let's see if I'm actually correct. So let's write a differential equation. The rate of change of y is directly proportional to the value of y. What letters can I use to write the rate of change of y? dy dx, that's fine, equals directly proportional to y. What is that going to look like? All right, multiplication of what and what? Y and our constant of proportionality. What letter did I normally use? Okay, sure, let's do that. All right, we're actually going to solve this one. There's going to be a heck ton of letters, but we can do it. So when we were solving, the first thing we had to do is what? Yeah, we have to separate our variables. So directly proportional doesn't just mean I equal it. It means I'm a constant multiple of it. So that k is a number. I just don't have enough information to solve for it yet. All right, so what's on the wrong side? The y, so I'm going to divide, and the dx. Now, with any numbers, which in this case k is a number, I'm going to keep it on the x side because usually I want to solve for y at the end. So the more stuff I can keep on the x side, the better. All right, well, what now? Yep, my 7th block realized you could say separate and integrate, which they thought was cute that it rhymed. So there you go. All right, how do I integrate the left-hand side? This should be immediate. Natural log absolute value of y. Anytime it is 1 over something to the first power, we've got a natural log absolute value. All right, what about the right-hand side? K is a number. Okay, k is not a variable. K is a number. Let's go kx. What else? Just take a moment to realize that we're doing so much math. There's like one number on the page. I love it. Yeah, we could even write it, well, y to the negative 1. Yeah, it makes it a little easier to put it on the x side because the y side has a more complicated integral, and eventually I'm going to solve for y, so it's much better to keep it on the x side. All right, I would like, can we solve for c in this case? No, what would I need? What information would I need? Let's go with a point, an initial condition. So instead, I'm going to do my last step of solving for y. I'm trying to find a general solution. So I would like to get rid of the natural log. How can I do that? E.
Yeah.
All right. So I'm going to go y equals. Ooh, I remember something weird happened when I dropped the absolute value bars. Plus or minus e to the kx plus c. Oh, you guys remember that weird algebra thing I did? Yeah, let's break this up into e to the kx times e to the c. What was the purpose of that? Yeah, I'm going to take all of e to the c, which we established e is a number. In the context of this problem, c is a number. Let's morph the plus or minus into it as well. And we're going to call all of that a letter. Now, someone who was in here this morning, I think Charlotte was in here this morning doing a question, and she solved for c in a problem that looked just like this, and she got natural log of 4. The number that she got to put in front of her e was the number 4. 4 is a nicer number than natural log of 4, and that's usually what's going to happen if we set this number here equal to a letter. Now, I've already used K in here. Does anyone have a favorite letter? A, sure. All right, I actually don't love the letter A, but it's because I am going to kind of recognize it. So we can write it as A, e to the kx. I'm going to use some different letters, though, because I think if I change the letters, I think you're going to recognize this solution. Instead of A, I'm going to write P. E, I'm going to keep itself. Instead of K, I'm going to write R. And instead of X, I'm going to pretend this is time, T. Yeah, did you guys do PERT at all? All right, does anyone remember what it was for?
No, I remember it.
Okay, so PERT. I always was so confused by why this came up. Yeah, Corey, do you remember? Yeah, it's for continuously compounded interest. So if you have like a bank account and it's collecting interest all of the time, so not like quarterly or every month or whatever, but it's continuously compounded, this comes up, which it looks the weirdest. And I was always like, because the compounded like annually or biannually, whatever, it's very algebraic looking. And then all of a sudden this E pops up and I'm like, what the heck is that doing there? The reason that pops up is specifically because of this, but let's look back at the differential equation. This says, let's go back to that bank account kind of example. The rate of change of my money with respect to time is proportional to how much money I have in the bank, which makes sense. I'm going to earn more interest the more money I have in the bank. So this is an equation. This solution is an equation that can model what's called exponential growth or exponential decay. Another good example of something that uses this formula or can use this formula, everyone's taken chemistry at this point, yes? Half-life can follow this formula. The amount that the rate of change of what you have is directly proportional to how much you have. So that is kind of the situation. So we're going to solve one question that has to do with this. And then we're going to move on to a better model that's going to be more complicated but more accurate. So let's talk about how to do this question. We are really going to do almost literally zero calculus. So we got a population of fruit flies, fruit fries, like the chicken fries from Burger King. It doesn't. Maybe I'm just hungry, Brandon. All right, so I've got fruit flies, and their population increases at a rate proportional to the amount present. If I read that sentence, essentially that sentence is this differential equation from the top. If I can recognize that I'm in a solution where the rate of change of what I have is proportional to the amount of stuff that I have, I can already go and say, I'm going to use PERT or whatever letters you want. Sometimes textbooks will use like CE to the KT. That's what I got taught with, but PERT we recognize. All right, so that's the calculus. I'm done calculus at this point. I've recognized that I'm in this situation where the solution is PERT. Now I'm just going to do some algebra. So let's read the rest of this, see what we got. There were 33 flies in the initial population. That's a 0.033. There were 100 flies after the second day. What point is that? 100. I want to know how many flies are present on the fourth day. So 4, question mark. So what these 2 points are going to allow me to do is solve for the 2 letters in my question that are actually like constants I want to find. E is a number. He's always going to be the same number. T and Y are variables, but P and R are constants that I can solve for. So which point do you think we should plug in first? 0.33. You need to plug that point in first because it will be so much easier. Let's see why. So I'm going to plug in 33 for y, p e to the r times 0. Do you already see why the 0 point is better to plug in first? Yeah. So we've got 33 equals p e to the 0. What is e to the 0 power? 1. So p equals 33. That is actually not surprising because p, does anyone remember in terms of like compound interest what the p stood for? Yes, it's the initial, it's for principal. I think it's that principal because principal is like Dr. Electoral. So principal. Yeah. So that's like the initial amount of stuff. So if I have 33 fruit flies or if I'm in a bank account, it would be like the initial amount of money. All right, let's go ahead and we're going to plug in our second point. So I'm going to plug in 100 for y. P now I can plug in 33. E to the r, and then my time is 2. Now, as I solve for this, this is not going to be my final answer, so I'm not going to pull out my calculator yet. I'm going to leave this r value to be super gross and weird, and it is going to be super gross and weird. I'm going to have 100 divided by 33. All right. How do I get rid of an e? Good. Natural log. To get rid of natural log, we did e to the power. So to get rid of e to the power, we do natural log. So natural log of 100 over 33 equals 2r. And now I'm going to divide by 2. Notice I am not finding a decimal at this point. This number is not going to be nice. It's going to be a weird number. And I'm just going to let him look super weird. He picked out a weird outfit today. I'm going to let him roll. That is not my final answer, though. So I need to leave it like that because I'm not going to round. E to the power of stuff, that changes very quickly based on small decimals. So we want to keep it unrounded. What should I do to find my final answer? Essentially plug it all in. So I'm looking for the y value. That's my question mark. My p was 33. E is himself. R is this weird, nasty number. And what am I plugging in for t? 4. I want to know on the 4th day. All right, let's see if we can all plug this into the calculator the same way. We will need a calculator today, so if you don't have one, grab one back. See if you can get a number rounded to 3 decimals. No, so we don't have to put it in absolute value like we do when we integrate for a couple of reasons. One, I know 100 over 33 is definitely a positive number here. And we're using this more as an inverse function. When we integrate, we're using a function, so we need to make sure that it works. Here, I'm just using it as like.
Natural is that automatically brings the power.
Yeah, exactly. So it's kind of canceling over that.
So that's just wrong.
The only correct response to that.
All right, remember how many decimal places?
Yeah. In the problem, it says hard to be hungry. So it's like over.
Good, my dad taught me how to count on the aircraft here. I remember 3 and 4 were different. 3, 1, 2, 3, 4. I can't remember. All right, we get a number.
How do you get to natural?
Natural log is on the left-hand side near the button that says actual log, near like 3 or 4, somewhere in there. Anyone get a number? 303 point what? Really? Ew. I don't like that at all.
And it actually keeps going in that pattern.
I hate that. All right. 303.030 what? Lies. Ew, I really don't like that number. All right, so I'm going to show you really quickly. Let me see if I can find a graph. Oh, we can see. Everyone say hi to Lily. She's on Google Meet.
Hi.
She's right here. See, it says Lily. Oh, I don't have my sound on. Lily, you can say hi now.
Hi, guys.
All right. So if I graph this, let me graph like y equals e to the x. Now, this is like the parent function of what's going on in my equation. Is this a good model for the amount of fruit flies in a situation? Is it a great model? It makes sense for a while, but then think about like if I keep zooming out. Let's say I want to go to day 200. Is that going to make sense anymore? No, we are not just going to like, if we're talking about fruit fries, I cannot say it right. Flute fries. And I talk about fruit flies in a population, eventually they're not going to keep growing exponentially. This doesn't really make a whole lot of sense as far as models go, but it's a very easy model to work with. So in a second, I'm going to give you a new set of notes that's for something called logistic growth. Now I want to show you what the model looks like, but as I type it in, notice that it's a lot more complicated than PE to the RP. Right. Well, you have to do the algebra. You just don't have to do the calculus to plug it in. All right. So I'm going to drag some of these things around. That's a boring one. Where does this guy go? What? Hold on. Oh, I need T to be a variable. Hold, please. There we go. All right, so this is kind of what a logistic equation looks like. So you can see that most of the time this A will be positive. That works like a principal. This guy can change whether I'm growing or shrinking. And this guy, the L, does cooler things. That kind of shows where the top of this is. But you can kind of see that this is going to model population growth or growth of a lot of things a little bit better because eventually things stop growing at some point. So if you think of population growth in Loudoun County, actually you can look at the population growth of Loudoun County and we're like around here. So we've been growing really, really fast, but eventually you can't grow with more people. You eventually run out of space, you run out of resources, you run out of something. But notice that this model compared to PERT is way more complicated. So while we get more accuracy, we lose like the simple computation. So I'm going to hand out some notes. We're going to talk about this model a little bit. The nice part about this is we're not going to be solving this differential equation. I used to solve it in class, and it was just the algebra to get y by itself is.
Like your class or like are you taught?
Well, I taught it. Actually, when I was student teaching, we made them solve it on the test, which was so mean.
You made them solve it on the test? Oh, yeah. Wait, did you ever have to solve it? You know, like
Probably. Teachers used to be way more mean to us when we were doing stuff. But we had to learn it. We had to learn this stuff. We really changed because we used to have to do this like word computation all the time. Your guys' English is way more about like I'm gonna read this big amount of paragraphs and I have to figure out what it means. It's actually really interesting. I look at the different words.
Which one do you think is better?
I don't know. Just different. One day we should really look at the 2008 test that I took. Like the last year's test. The amount of all right. So let's talk about logistic growth. I would love to get through the first page front and back and then take a break. I will tell you, I'm going to do a lot of stuff to explain why the couple of very discrete pieces of information work the way they do. And then I'm going to talk about what actual work do I need to show, because it's actually very small. So let's talk about logistic differential equations. If we get done early today, I also have a very fun activity, but I want to make sure we do this part. So logistic, it only takes like 5 minutes. Logistic differential equation. So what this allows us to do is oh, you know, the copiers have just really been out to get me. What? Okay. Who has just one page? Anyone else only has one page and not All right. So let's look at this differential equation. So here's like it written out in word form. We have the rate of change of a population of a system is jointly proportional. So that means we have two different factors going on. We've got this P and this fraction thing. To the population, that's what we're calling P, and the difference between 1 and the quotient of the population and the carrying capacity. So let's talk about all of those words. We're going to talk about where they're coming from, and then I'm going to show you there's kind of 4 things you need to be able to do with this. We're going to walk through them. So P is our population. A lot of the times you'll see like in real world stuff, you'll see like a population of, we're going to do deer, or a population of bears, or a population of plants, bacteria. A lot of the time it's going to be living things. This is K. That is our like proportionality constant, but you can also call this, some things call it the logistic growth rate. So it kind of gives me a speed at which things are growing or shrinking. This L is probably the most important number of our entire situation here. Pretty much everything is going to rest upon us figuring out what that letter L is. That is what's called our carrying capacity. That's a really fancy way to say, like, if I take this population forever and ever out to like time infinity, what's the biggest amount of things I can fit in this space? So like in this classroom, our carrying capacity might be like 30. If I get over 30 people in here, people are gonna have to leave. Yeah. So that would be kind of a speed at which we're growing. So you're going to notice here, we're going to use this 40% per year here. Usually that's going to be a constant that we'll solve for, just like the R in the PERT equation. So we'll get information to solve for that. Usually we don't have to like find that out. All right, one thing I want you to notice about this differential equation is not that K, this 1 right here. That L is very easy to find if that number is a 1. So a lot of the time when we're working with this differential equation, our goal is going to be to make that number 1 so that we can identify the pieces in this differential equation. Yes, exactly. So L is very easy to find when that number is 1. So we're going to work on that a lot. What? The L? The 1, it's just when I'm factored this way, L is really easy to find. All right, so the model for this, so if I went through and actually solved this, I would get this as my solution. You do not need to memorize this. What I'm usually going to do with this, or actually the really only thing I'm doing with this right now, is I'm going to be using this solution to justify why some of the facts that we're going to know about the logistic differential equation are true. So I'm going to do these like first 4 questions, kind of the long way, if you will. And then I'll go back with like a very shiny pen or something, and I will put down like the work that you would need. Austin. We're usually going to solve for it. Yeah, a lot of the time when we do questions like this, let me kind of scroll down. A lot of the time, we're going to be asked very specific pieces of information where we're actually, this doesn't really help to look at. A lot of the time, we're going to be looking at things where that rate is already like in there. So if you look here, that K would be like a 10th, or it's going to be a number in there already. If we were working with a solution, we could get a point and we could solve for it, or we might be told it. But most of the time for this stuff, we're actually going to be working with the differential equation and not the solution. So the K isn't going to be something we're really worried about most of the time. So I promise to be very clear about what I'm going to be asking you about. Give me like 2 seconds to make sure we're on the same page. All right. So again, I'm going to do these questions working through with the solution, but I'm trying to motivate. There's very discrete facts that we're going to need to know, very specific facts that are like very specific questions that get asked all the time. So we're trying to motivate why we can memorize the way to get them. It will make sense in a second, I promise. So we're going to work with this deer population. They're in a 10,000 acre forest. I don't really care how big the forest is. There's just some deer in it. Has a carrying capacity of 1,000 deer. So I already know that L is 1,000. I am going to assume the deer population grows logistically. One of the nice parts about logistic differential equations is they're really going to come out and tell you that it's logistic, because it's a very specific differential equation, so we can look for that word. This one is going to give us that growth rate of 40% per year. So this is a positive growth. And instead of using the number 40, I'm going to use it like a decimal, like a percent. So I'm going to call it K.4. All right. So we're going to find a model for this differential equation. So we're going to kind of work to find the constants in here. Mostly the only one I'm missing is that A. So we're going to find that one real quick, and then we're going to use that model to justify why we can find the next 3 things. So if I were working with this differential equation here, if I wanted to write it with what I've got, I would still have dp dt. I would have the 0.4 in for my K. My P would be here. I'd have my 1 minus P over my carrying capacity, which I've identified as 1,000. Now I could separate and integrate this, but you actually don't have the tools to integrate this yet. You would need something called partial fractions, which we'll learn in our unit 7, which is all about integrating. Actually, integrating this isn't too bad, but when you go to solve for like P equals, the amount of algebra you have to do to get to this solution makes it something that's not really accessible for our AP test, which is why all of the questions about this differential equation really focus on identifying numbers out of the differential equation instead of from the actual solution. So what we're going to do is we're going to try to solve for the letters in here that we don't have. We're going to plug in 1,000 on the top. We're going to keep 1 plus A is something I don't have, and then I'm going to have e to the negative 0.4t. So I'm just plugging in the L and the K from my differential equation, which I got from my question. All right, I have an initial population of 100 deer, which gives me a point 0, 100. So just to flex our algebra skills a little bit, let's go ahead and try to find A. I'm going to plug 100 in over here. 1,000 stays. I hate people. Oh, I forgot I'm recording this. Sorry, Lily.
I hate people too, if that helps.
Did you hear that? Did you hear them scream?
Kind of.
Okay. It was real loud here. All right. Yeah. No. So we're really, the 3 questions I'm going to ask you are this one, and this one. I don't want to just tell you how to get them. I want to show you how to get them with the solution, but eventually you're going to kind of know them as 3 separate facts. Just trust me. Trust me for about 5 minutes. I promise. All right. I would like to get A by itself. I think e to the 0 is 1. So I've got 1 plus A on the bottom, 100 on the side, 1,000 on the top. How do you guys want to get A by itself? Yeah, it's e to the 0. All right, I'm going to multiply by 1 plus A. Thoughts now? Cool. Dividing by 100 is pretty smart. You could also distribute the 100 if you wanted to. That's going to give me 10. So A is 9. So if I actually wanted to look at this solution, I could have this guy right here. Now, this is going to help me motivate my discussion of the next 3 questions. For logistic, you're really going to be asked 3 questions over and over again, but I want to show you why the answers are the way that they are. I think you deserve to know why the answers are the way that they are and not just have me be like, you just do this for this question. So let's go ahead, and I actually want to go.
Wait, so the answer is
Yeah, we're looking for a model, so we're looking for an equation. That is our equation. Correct. If I want you to find a model, yes.
So we put the likelihood of a sequence.
I will show you exactly what questions you'll be asked.
Okay.
All right. So our model is going to look something like this. Oh, look at this guy. He's so tall. Let me give a window. All right. So on the x-axis, maybe like 0 to like, let's go like 50 years down the line. Y-axis, I'm going to start at like 0 because we always have some deer. And our carrying capacity was 1,000. So let's go up to there. I'll zoom out a little bit. All right, so here is our model right here. You can see the y-intercept right here, 0, 100. That's our original amount of deer. We've got this growth pretty fast right around this point, and then we kind of level off as we get to the carrying capacity. We're actually never going to go past that number. We're always going to be right around there. So let's first figure out how long it would take the population to reach 500 deer. What would I want to do with my model that represents the number of deer and the number 500, the number of deer that I would like?
Okay.
Plug in 500 for a P of T. Good. I don't want to plug it in for T because that's some time. So I'm going to plug it in on the left-hand side of this equation. So 500 equals 1,000 over 1 plus 9 e to the negative 0.4. Should we solve it by hand just for fun? All right, then how would I do it on the graph? All right, so I have this guy graphed. I want it to equal 500. What else could I graph? I could graph y equals 500, and what would I be looking at on the graph? The intersection point. Remember on your TI calculator, we could do second calc intersect, enter, 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 and we want this value right here, 5.493. So we could get T equals 5.493. Cool, so I can work with this model. Wonderful. The next, yeah, Mason. Probably not, because the next 2 questions are the questions that you really need to know how to do.
Wait, for the graph,
Mm-hmm.
what did you graph?
The model, this guy. I just have all the letters there, and I just plugged in the letters.
Oh, I saw that and I. So what if P of T stands for
The population of deer. Mm-hmm. All right, here are the 2 things you need to be able to know how to do. I'm going to show you why they work the way that they do. You're good. All right, I'm going to show you why they work the way they do, and then we're going to practice a little bit with how I could get them without doing all of this model stuff. So the 2 questions I need to be able to answer about logistics. As we go forever and ever in time, What is the limit of the deer population? The second question we need to be able to answer is when is the deer population growing the fastest? Those are literally the only two questions that get asked about logistic. They're almost always on the multiple choice. So we just need to be able to answer these two questions. I want to show you why they are the way they are. And then all of these questions at the end are like AP practice questions. So we'll do as many as we can before the end of the block. So let's look at our model as time goes to infinity. Now, can we actually reach infinity? No. What kind of calculus do we use when we want to get somewhere but we can't actually reach it? Limits. So I'm going to take a limit as t goes to infinity of the model we had on the front page. This is a good throwback. Oh, nice. What a great time. Oh, I should have a 4 there, not a 9. All right, so I'm grabbing this from the front, but I'm mostly just motivating a fact here. You actually already know what this is called. I just want to show you how we get it. So let's focus on this part right here, the only part with variables. I want to know where this thing goes as t goes to infinity. Anyone know already? What do negative exponents mean? Where could I move a negative exponent to? Let's go to the bottom of a fraction. All right. As I plug in infinity to that exponent's getting super huge, aka going to infinity. If I take e to the power of infinity, that's getting super duper huge. So I'm working with something that looks like 1 over infinity. Where does that trend towards? Can someone say it more confidently? Excellent. So as I plug this in, 1000 is trending towards itself. 1 is trending towards itself. 9 is trending towards itself. And all that stuff I highlighted in yellow is trending towards 0. So this turns into 1000 over 1, or 1000. Now, we already had a name for the number 1000 in this question. What was the name of that? Carrying capacity. So this is a different way to ask for the carrying capacity. I wanted to show you why that works in the model. But really, if we can identify the carrying capacity, we can answer the answer to this question. So it's a different way to ask for carrying capacity. As time goes on forever, what's the limit of the deer population? It's just the carrying capacity. We can identify that from the differential equation. So while I wanted to show you why it works from the model, we can identify it without using the model. All right, the other thing we need to be able to find is that when the deer population is growing the fastest. This is a weird question to talk about. So I want to talk about what it means first, and then we will do some math to find our fact. So growing the fastest. It's a little bit of a weird question. I want to know when the rate of change is essentially the maximum. So I want to know where this graph has like the steepest slope on this graph. Where is this graph growing the fastest? Does anyone have like a guess of where it's growing the fastest? Where do you think? All right. So somewhere, it's probably somewhere in here. So it's not growing very fast here. It's not growing very fast here. Does anyone think they know exactly where? Awesome. What do you think? All right, 500 this way? Or 500 this way? All right, so you're thinking like the population at 500, somewhere in here. So it looks like around that point. Let's see if we can prove that with some math. We're going to do another throwback to kind of prove that. So I'm going to take the differential equation we made, the 0.4 p and the 1 minus p over 1000. All right, if we want to see where we're growing the fastest, we want to maximize the rate at which it's growing, which is dp dt. Ooh, yes, maximum. I love it. How do you find a maximum? My AB class is learning this right now. I give you a function. I say, find me the maximum. What? I know. Find the critical values. How do I do that? Set what equal to 0? If I just give you a regular function, I say find me a maximum. How do you find its critical values? I need a derivative, and then I need to set it equal to 0. And I need the derivative of what I'm trying to maximize. So I actually need the second derivative of this function. So throwback Thursday, let's do a second derivative implicitly. What rule do I need to use on this? Product rule. Yeah, this is a really fun derivative. All right, so first, derivative of the second. Derivative of 1 is 0. This guy is like negative 1,000th p. So I'm going to have negative 1 over 1,000. And what's the derivative of p with respect to time? dp dt. Plus second. Derivative of the first, derivative of 0.4p, 0.4 dp dt. All right, we have two large terms right now. I would venture to say they have a lot in common. I would like to factor some of those common things out so that when I set this equal to 0, it's easier to set the factors equal to 0. Of the two things I have underlined in red, what things do you notice they have in common? All right, they have a 0.4 in common. Anything else? They both have a dp/dt in them. All right, let's factor both of those out. From the first term, I have negative 1 over 1,000 p. From the second term, I have the stuff that's in the parentheses. So 1 minus p over 1,000. All right, if we're thinking about setting each of these factors equal to 0, this first one, 0.4 equals 0, nonsense. They do not equal each other. The second factor, dp dt equals 0. Well, we were trying to maximize dp dt, right? Would it make sense that the maximum rate of change is when it isn't changing at all? No, probably not. So we're not going to use that one either. So I'm putting all my money on this guy right here. All right. I would like to combine like terms. Anyone see any like terms? Yeah, I got this set of p's. Next set of p's. So like negative 2 over 1,000. That works. P. Yep. Let me rewrite this one a little bit. So I have negative 1 over 1,000. Negative 1 over 1,000. Negative 2 over 1,000. 1, 2. Plus 1. I'm setting that equal to 0. What? Uh-huh. Mm-hmm. All right, I'm going to add those p's to the other side. And I'm going to multiply by the reciprocal. So I'm multiplying by 1,000 over 2, which is indeed 500. And since that's a p, that's 500 deer. Now, I'm going to tell you that works for every single logistic differential equation. That if I choose to find the second derivative and find my critical values, set them equal to 0, there's going to be one critical value makes sense. And it always is going to be my carrying capacity, which in this case is 1,000 over 2. So realistically, what work will you actually show? You're going to say, okay, my carrying capacity is 1,000. I'm going to say growing fastest at 1,000 over 2 equals 500 here. So all that math we did is just to justify a fact that we will now know. We are growing the fastest at 500 here. Now, if I wanted to know what time, well, we kind of already did that. If I scroll up, we could set 500 equal to our model. But like I said, we're usually not going to deal with the model for AP questions. So usually we'll be asked the population or maybe the rate of change, but we'll talk about that in a second. Okay, so can you find the carrying capacity? Can you find carrying capacity over 2? That's really all it is. Let's look at a couple of multiple choice questions before we leave. No. We have no time for a break. All right, let's look at this guy. Lots of stuff going on. Next class's notes are like the shortest ever, so don't worry. We have n satisfies logistic differential equation. Does this look like a differential equation that is logistic? Yeah, we got an n and a 1 minus n and a fraction. Does anyone already know what the carrying capacity is? Good. L is 850. All right. When are we growing the fastest then? Which is what, 425? All right, let's look at some of these guys. So would you agree this should be a t right here? As t goes to infinity, if I actually found my model, would I get 850 beer? As t goes to infinity of my model, would I get 850 beer? Yes, that's the carrying capacity. Oops. Yes, this is asking for which one's false, so that is not our answer. All right, the NDT, our rate of change, has a maximum value when n equals 105. Is that true? Is the rate of change a maximum when n equals 105? No, when is the NDT having a maximum? At 425. So that's my answer, but let's keep going. The n, our second derivative, excuse me, however you say that, equals 0 when n equals 425. Is our second derivative 0 when n equals 425? Yeah, actually, what? Yeah, it's a critical value of our first derivative, but also look at the graph. What other thing usually happens when our second derivative is 0? When it changes sign specifically. A point of inflection. Look at this graph. Isn't this graph going from concave up to concave down right at that point? Heck yeah, it is. So that point of inflection, that's happening. So this guy is true. All right. And this is saying when n is greater than 425, so we are above that critical value, that kind of point of inflection on that graph, our first derivative is positive and our second derivative is negative. So that means that our first derivative is positive, so n is increasing. Our second derivative is negative, so n is concave down. If we look, increasing. That's concave. So knowing the shape of this graph is also helpful. Mm-hmm. Yeah, and you can watch me move this around as much as you want. Well, A won't be negative. Yeah, I know. And then K, we could move this. This will just growth rate it. All right, let's look at the next one. Be cool. All right, number of students in a cafeteria. Woo. Oh, I sat on the new furniture yesterday. Nice. All right, we've got this logistic differential equation. Anyone notice anything interesting about it? Yeah, it has some stuff in here. So our 1 is not there. All right, we've got P of 0 is 25, so an initial amount. We want the greatest rate of change in number of students per second of this guy. So what's our goal here? If we want the greatest rate of change. All right, when it's growing the fastest, so we need to identify our carrying capacity so we can put it over 2. Now, the 200 is in our way. How could we get rid of the 200? Kind of. We are going to divide that, so we're going to make it into 1 by factoring it out. So we're going to pull the 200 out, but I like that Brandon said dividing. When I factor this out, it's like I'm dividing this 200 by 200. So when I put this P over here, I also need to divide this guy by 200. So by factoring it out, I can make that into a 1, and my P is now in a fraction. So it's like I'm multiplying by 200 and dividing by 200. So if I redistribute this back in, what? So it's like I'm multiplying by 1, essentially. Let me write this a different way. All right, so pretend I am multiplying by 200 over 200. Legal, yes? All right, I'm gonna pull this 200 to the front. And I'm gonna divide on the inside. So 200 divided by 200 is 1. So this 200 is going here and here. All right, now that I factored out that 200, can you see what the carrying capacity is? What is it? Am I done? Yeah, our carrying capacity is this bottom number. Am I done? What does the 100 represent? This is a number of students, right? It asked me for the greatest rate of change. So that gave me a number of students. How can I find the rate of change? What is the rate of change asking for? What thing on this page represents rate of change? dp/dt. Couldn't I now plug in 100? Yeah. So I've got 100 over 2,000 times 100 from the 200 minus 100. Let's get rid of some zeros by dividing by 10. So I've got 100 divided by 20, or 5. All right, last thing before we leave. Yep. All right, we've got a logistic differential equation. It looks like this. I want to know which graph goes with it. Which ones can you already cross out? All right, B doesn't look like a logistic that is growing. Which other one? C doesn't look like a logistic. A also doesn't. This one looks like PERT, to be quite honest. All right, why do we know this one is the good one? It has a carrying capacity of 500. It's got that S-shaped graph. We are good to go. You don't even have to really do anything. The most math you're going to have to do is factoring out a number. So we are going to practice more with this next time. before we leave, we have about 2 minutes. Let me be clear about what's happening next time. We have one section left to learn. It is the easiest thing in the entire world because it's just tangent lines. So the notes will not take very long at all. We have not gotten to do any notes checks yet this kind of unit. So we're going to do some notes checks next time, some work on this. I'll probably check them as you go to make sure that you are feeling good about this because I would like to do an assessment on Wednesday. I am probably going to post a review over the weekend that's going to look so similar to the assessment that you're going to want to do it. Michael. If you're doing the problem set, I'd recommend trying some of it by Wednesday, but I'll take it anytime before winter break. Ashley. I would just check the notes online. Yep. And if you want, I can record the class if you want or whatever. Just let me know. Did someone just straight up leave? Oh, no, never mind. All right. Thank you guys for your hard work today, and I will see you next time.
And I know
What's me too, Lily? Oh, you hate people? That was a long time ago. Bye, Lily. Mm-hmm.
I sent you another email from Georgetown.
Okay.
Honestly, like, they're not common enough for